Okay, ladies and gentlemen, let's do gradients in 3 dimensions. I promise this is not actually very different. Okay?
Yeah, I was going to say, don't you just add kind of a z variable of f df dz? Or del
Yeah.
f del z?
So, recall, this thing is a nabla. As Rayler pointed out to me, I am an idiot. And I amalgamated something from a South Park episode with, so yeah, that would be a nabla, not a nambla, which is, yeah, a different disgusting thing.
I've heard people call it a del.
A del? A del is,
That's a delta.
yeah, this is a delta. Some people short,
That's a del.
this thing?
Yeah.
Some people call these dells.
No,
Yeah,
I've heard people call the upside down delta a del.
okay.
But I guess there's a lot of people out there.
Yeah, these things, this guy and this guy, are both derivatives of the delta symbol,
Okay.
right? And so they get a variety of names. They're not, neither of them is actually a symbol in a language, right? So they have these kind of funny names. I'm going to call this one a del and that one a nabla, but what?
Wikipedia says the right one is a del.
This one?
Yeah.
Bull.
Well, that's an upside down triangle.
Okay.
Nabla is more like a right triangle.
Whatever. I guess we should standardize. We'll call this one a partial. And we'll call this one a nabla. And now we're all standard and we shan't use the other thing. Cool. And if you hear the other thing, just look it up on Wikipedia. Cool. Good talk. So, nabla f is, right? And from last time we called this partial with respect to x, I plus partial with respect to y, j, right? Okay, so I'm going to say it's that, maybe plus the partial with respect to z times the k vector. Okay, if I had to describe gradients in 20 dimensions, what would this symbol mean in 20 dimensions? Oh, I need to multiply this by a function f. Since I had an f over here, I should have an f over there.
Because in 20 you just have like the rest of the alphabet, right?
No, you just kind of do
Yeah, so
X1.
when we go past 3, right,
X1, X2.
we do x1, x2, x3, x blah, 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 right?
X3.
So if I wanted to do this nabla thing in lots of dimensions, I would do partial with respect to x1 times the x1 basis vector plus the partial with respect to x2 times the x2 basis vector, and so on until I got to the kind of end, right?
X to the n.
Which would be xn and the xn basis vector. So this would be nRn, right? Thought of as a vector space. You guys all cool with this? Okay, so this is the generalization. Now, why are gradients useful?
We can use them to calculate directional derivatives.
Good, cool. We remember that we learned directional derivatives earlier today. Okay, so that would be if you want to do fu at AB, right? What was our formula? I think we should do the derivative information for f, right? So that would be the gradient of f evaluated at the point AB. And then I want to point that in the u direction, so I dot this with u. And what do I need about u? Yeah, u better be a unit vector. Why should u be a unit vector?
Otherwise you'd just be scaling up your gradient.
Yeah, right? This is a dot product. You guys all with that?
Yep.
The dot product contains both the length information of the two things and the cosine of the angle between them. the length information for the derivative part here, the gradient, right? That's useful. That tells me how frickin' steep this thing is, yeah? But I don't want the length of this u vector to come into play, right? I just want to know how much the gradient points along u. You guys see that?
Okay.
So I want the length of this thing, not the length of that thing, and then the cosine of the angle between them. Cool? So that thing better be a unit vector so that doesn't accidentally come into play. What if I want to take a derivative along something that's not a unit vector? Yeah. Make it a unit vector, right? Divide by the length. Or take this dot product, right? And then just divide whatever you get by the length of the vector you put in there. You guys cool with that? Okay, so this is directional derivatives. Now, cool fact. Super cool fact. When is the directional derivative the greatest? What does that mean? And why are gradients awesome? Okay, so first, when is fu biggest?
At the point you're evaluating the function. Right.
Yeah, so for a given point, when is it the value of fu biggest?
At that point you want to be.
You were saying this earlier, like it does mean something about like that point in the slope or something like that.
Okay, how about this? So let me just, to get everything out there, I'm going to fix a point A, B, and then I'm not going to write it down. Okay, so we're talking about at one specific point, right? So in R2, right, that would look like, here's a point A, B. Don't care where this is. There's some contour map going along here, right? Follow this? When I evaluate f, so when I do gradient of f, right, and evaluate it at a, b, what kind of a thing is that?
It's
That's a normal directional derivative.
So this is a, right, this is the fx and fy evaluated at ab. So first, what kind of beast is this? Is it a scalar? Is it a vector? Is it a sheep? Is it a dragon? This is a vector, right? Gradient of f is a vector function, right? It's got x's and y's in it. But once I evaluate at that specific point AB, this beast here is a vector. You guys all with that? Let me say, just for kicks, that that vector looks like this.
okay.
Right? I have no idea what it looks like. It could look like literally anything. Right? Well, as long as it's okay. So, how do I calculate a directional derivative from that information? What do I do? Like, say I had a vector u that I was interested in. This part is not going to work. Kind of. Not really. It's okay, because I don't really care. So say there's some... That was close.
It was.
So say there was some vector u that I was interested in the derivative along that direction, right? How would I actually calculate that?
Oh, yeah.
I would take the partials, right? Get the gradient vector, evaluate it at the point. That's this blue vector that I've drawn, right? And then what would I do with the blue vector and the orange vector?
Dot them?
Yeah, I would dot them, right? Like that's what we just said you do with a directional derivative. Right? You take the gradient, you evaluate at your point, you dot with the unit vector in the direction you're pointing. You guys all cool with that? So, fu, right, at AB is the gradient of f evaluated at AB dotted with u, which is, what was I muttering earlier about norms and cosines?
It's
or magnitudes and cosines? This should be the magnitude of, yeah, magnitude of grad f evaluated at AB, right? This is just some number. Times 1, that should be the length of u, right? Times cosine of theta, right? What's theta?
Angle between the two.
Theta is the angle between what two vectors?
U.
Gradient of f evaluated at AB and u. You guys see that? Okay, so if I think about rotating that little orange vector, right? When is that thing the biggest? When is this quantity biggest?
Exact opposite.
Yeah, when they're parallel, right? When theta is 0, right?
Oh.
Cosine of 0 is 1. That's the best you can do for cosine, right? Okay, so when is FU biggest? So that was question, right? Answer, when U is parallel to what?
Now below F.
No.
Yeah, the gradient of f evaluated at AB, right? In other words, what did FU mean? If you're standing at this dot, FU's the directional derivative, right? So that's telling you how steep it is in the direction you're looking. So like you're standing here and you're gonna twist around in a circle, right? And I'm asking, when is that value biggest? What's that telling you?
Like the largest slope of that one.
Yeah, that's like walking around and saying which direction is steepest uphill. You guys see that?
Oh, okay.
So when U is parallel to gradient of f, right, is the biggest that thing can get, and the interpretation is gradient of f evaluated at AB points uphill. And better yet than uphill, it points at the steepest uphill. You guys see that? Further question, what does that mean it's perpendicular to?
Where it's, I feel like, where it's flat?
Yeah, right? It should be perpendicular to the flat spots. So the gradient of f evaluated at AB is perpendicular to the contour line. Or surface, depending on which. You guys see that? Depending on whether you get contour lines in 2 dimensions, right? And contour surfaces in,
3 dimensions?
sorry, you get contour lines in 3 dimensions, right? You have a function of 2 variables. And you get contour surfaces when you have a function of 3 variables.
Okay.
You guys see that? So the gradient points in the steepest uphill direction. Cool? That is what I would like you to take from this. It also helps to know that it's perpendicular to the contour lines and surfaces, because that lets us get tangent planes to annoying shapes. Like shapes that aren't the graphs of functions. Like we can get tangent planes to spheres using this idea. Because this thing would be a normal vector, right, for that contour surface. Does that make sense?
Yeah.
Okay, cool.